All right, welcome back, everybody. The inspiring talks from this morning reminded me of some quotes from another inspiring person. Arthur C. Clarke is one of the co-authors of 2001 Space Odyssey and many great science fiction novels. The three quotes that come to mind are here. The first one, I'll read it in case it's a little bit small. When a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he's very probably wrong. So please keep this in mind about everything that we say today. Even though we may not be elderly, keep in mind that when we talk about boundaries between what can be done and what can't be done, we don't know if the conditions for these statements are going to be satisfied in the situations that you look for. And a lot of progress is made by pushing these boundaries. So please keep that point in mind. The next one says, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And this is a place where modeling, the subject of this talk, and also simulation are going to be very useful. Because modeling in many ways is going to allow us to create the worlds that we're interested in exploring and to see how far can we go with different assumptions and what we can do under different circumstances. And the last one, that was the one that really came directly from Martin's talk, says that any sufficiently advanced technology is indistinguishable from magic. So this is something that CPS will do in many cases, whether it's autonomous vehicles or other technologies. And part of the challenge for us, the ones that are interested in building these things, is to really understand all of the different technologies that are coming together to create these cyber-physical systems. And this is something that, again, with modeling, we will explore how we can do it ourselves today. Now, speaking of magic, Martin also talked about situations where the definition of CPS might vary depending on where you come from, whether you come from manufacturing or from computer science, for example. One way that I explained to myself this magic that's happening today is the price of semiconductors. It has really been going dramatically down, and it seems to continue to go down. So apparently these are market prices, and these are indicators of cost from this particular statistic. There are many other similar statistics that continue to be published by different sources. And what this is doing is that it's making computing so cheap that it's going to be very easy, becoming easier and easier to introduce it in all kinds of contexts. One example that we have talked about today is the phones, the iPhones, for example, and the smartphones. But in the future, the Internet of Things, we're going to see technologies of all kinds of sorts and types being augmented with computing powers that will make the functionality, add to the functionality and add to the value of these things, but also complicate how we control them and manage them. What do cyber-physical systems look like? There's a lot of examples presented on this slide. To me, I'm a little bit of a traditionalist when it comes to cyber-physical systems. A lot of my research, maybe over $5 million worth of research, was funded by the National Foundation in Sweden, in the US. And there, in the call for proposals or projects for the Cyber-Physical Systems program, a lot of times the keywords that were being used were a cyber-physical system is made of computational components, physical components, and these are networked together in some way. Now, over time, I came to realize that these are actually very interesting words that are used in this classic definition that one can read from the call for proposals. Probably it changed over time. I haven't surveyed all of the different calls from the Cyber-Physical Systems program at the NSF. But what's really interesting about these three is that many things can be the same thing, can be all three. So one device can be a communication device. It can have physical characteristics. It can have computational characteristics. In fact, in many cases, if we look closely, there are many things that have these three characteristics. So what are we talking about? What is this business of CPS being a new thing? Well, again, as Martin said, it's not entirely new, but what's really important here is the perspective. So if we think about computational components, we usually think of things like computer science, computer engineering. There's a lot of results, techniques, methods, engineering approaches that are developed within areas that relate to computation. And again, when we look at physical components, and we'll talk about examples of these things, there's a lot of disciplines and processes and methods that are developed under these umbrellas. And again, communications, a similar thing. And to some extent, they have been separated. And so what's interesting with the developments that we're seeing now is that they have to come together. And we have to be able to communicate well and work together across these traditional disciplines, and also be able to use the same formalisms, use the same techniques, use the same language, formal language or modeling language, and sometimes maybe even share the same tools. Another aspect or perspective that we see more often now of what is a cyber-physical system is that there's a computational part, a control part, and a communication part. In some ways, these are also representative of the disciplines that are often involved, more than what the thing itself is. So when you look at these definitions, think more about the approaches that people use to build them, build cyber-physical systems, rather than what is actually there in the cyber-physical system itself. Okay, so now we're talking about modeling cyber-physical systems. Why do we want to do that? We want to do that primarily because we want to build better cyber-physical systems. As we have this flood of new hardware capabilities that we can put into all kinds of things, how do we make sure that we're doing a good job? How do we make sure that we're building trustworthy systems? So in many ways, it's really all about ideas. So we have this device that's called a phone. We have a device that is called a music player. We have another device that does something else. And then we have this great idea, like, what if we put all of these things together and connect them to the internet? And then we get a smartphone. And then we have a whole revolution as a result of this thing. How do we go from the idea to the product? And here in this picture, I'm trying to illustrate the ideas by the two orange pictures at the top. And then the product, let's say, a windmill, an electric wind turbine. Okay? Now, how does this work? Well, there are people involved, for sure. These things don't make themselves. Okay? And at the same time, as we're thinking about these things, we come up with different representations of the things that we're thinking about. In one case, we think about, oh, well, there was this windmill concept that was very useful for pumping water. And in other times, we're thinking about, well, there's part of it which is a transformer that has to be managed in a certain way. And there's a control part, and so on and so on. And maybe, you know, it reminds us of, at some point, it reminded us of the electric dynamo. Maybe the wind turbine was the part of the idea of the dynamo on the bike, and the windmill. So there's a lot of different kind of pieces of this concept that we come up with, that we discuss, that create this idea. And then the key thing about delivering the product at the end of the day is about how much time it takes from having this idea to getting it out there. Yeah? Now, there's different processes, and during the day, I heard at least one mention of the waterfall model, for example, and there's many different engineering processes. Sometimes people say process is dead. Okay, there's so many different processes, you know, there's no more process. We just get things done. And we're not going to worry too much about how we do it. Well, whatever our position on process is, the key thing is, even in the absence of process, or even under, you know, assumptions of different processes for development, what will always be there is people. We're going to be involved in building these things somehow. And we need to communicate the ideas and to each other, and we also need to communicate to tools. If we're using a computer or a CAD tool, which are becoming more and more important, we have to have a good way for doing that. So communication, you could say this is what I postulate, my thesis, is really central. Communication of ideas in particular is really central to the development of any product, including cyber-physical systems product. So how do we communicate? Well, this is where models come from. And it's really interesting. If you go to the Merriam-Webster dictionary and look up what is a model, you'll find a whole bunch of definitions. And it's really hard to find something that fits the same definition, but if you look hard enough, you will find it. Basically, the way I'm going to define models today is that they are just an expression of an idea. Very simply. So we have an idea in our mind, and we express it in some way. That is a model. So if I draw a small painting on the board, that's one model. If I express the idea in mathematical terms, that's another model. If I use Simulink, if I use whatever tool, as long as it's a way for me to tell you what the idea is, somehow, then it's a model. So if communication is really important for working effectively, then models are very central. And this is why it's useful for us to reflect on what they are and to think about them and to see how they can be different in the future from what we use today. So in this picture here, I have some informal drawing of a windmill, another one with some physical dimensions. Here's an equation for how power is generated, how much power is generated. Another representation here is of the control system for a wind turbine. All of these are models. Now, models can vary a lot from being something very informal that just gives us an idea based on a lot of background information that we have, to mathematical models. And then something that's becoming increasingly important if we want to investigate this model computationally is that it's executable. Okay? And executable can actually mean all kinds of different things. It can be something that we can simulate. It could also mean, in a more abstract sense, something that we can analyze with a computer. Okay. All right. And one last thing is the idea of a model can actually be fairly generous to include both the idea itself from the very beginning until the product. Remember that at some point we used to have like mock-down models. We can even say, well, this particular product is a model of the line that is generated. Yeah, the whole product line or of smartphones in general. So it's a very useful concept that we can use from the beginning until the very end of the production life cycle. All right. Trustworthiness is an important theme for our summer school this year. What kind of things would affect trustworthiness? Or let's say, for example, if we consider safety. So we'll think of these things as a basic collection of properties or features that we may be interested in modeling. So geometry and shape tend to be important. And one practical reason for that is that one of the most common and straightforward ways to talk about safety is where something is. So if I have two cars that are on the highway, the fact that they are apart from each other is an indication of safety. When they stop being apart from each other, and if they collide at a high speed, then that is an indicator that something is unsafe is happening. Okay? So geometry and shape are important. And also for practical reasons, that usually gives us a way to visualize and imagine what's going on. Another aspect that's fairly broad, especially it's part of the reason why we call these systems cyber-physical systems, is physical nature. And this could be a whole range of things. And often we think of physics or physical aspects as mechanics and electromagnetics, for example, or thermodynamics. But other aspects such as chemistry can be important. Yeah? So if your device rusts over time, that's a chemical process. And that's something that you want to be thinking about. And mechanical engineers, of course, think about these things. So they're thinking about a chemical model of the system. Another aspect is computation. And that can encompass both algorithms and communication. And computer science and telecommunications are complete disciplines that provide us with different kinds of models for these aspects. And finally, one kind of less isolated aspect is time. So one of the surprising things to many computer scientists is that at some point, this software is going to be embedded into a system that has to operate in real time. And how much time the computation takes can have very significant effects on how the system is working. So one way that we can reason about the safety of a system, that's actually often a critical thing to think about for the safety of a system, is how do these things operate in the context of a common real valued notion of time. So that's a very important thing for us to have when we're modeling cyber-physical systems. And more generally, it's not just going to be time that is real valued, but often we have many real valued values as well. And this is a little bit of, in a way, if we come from the physical side, this is not surprising. If we come from the computational side, this is a big deal, because discrete sets are very different from real valued spaces, and they have very different properties. Okay, so the math is going to look, in at least the most basic setting, like something like this. There's the naturals. There are maybe fractions, but also reals, which are a space, a topological space. And then we're going to have variables. That's going to be another key ingredient for our models. We'll have functions like sine and cosine, which turn out to be particularly useful when we're talking about things like in 2D and 3D. It's very hard to talk about things in 2D and 3D without using them. We can, to some extent, with algebraic, purely algebraic specifications, but even those are nonlinear. Yeah? And then we have functionals, in particular derivatives. And if we are familiar with movement and speed and acceleration, those are very natural, and those have an important place. In addition, it's important to have, and very useful to have, equations. More importantly, we'll find that we'll need conditional equations for a variety of different reasons. Not the least of which is that sometimes discrete events happen, but also it can also be very convenient. In fact, most of the cases are convenience. Otherwise, it becomes very difficult to model these things. One of the really helpful things, for example, that people who build airplanes use is it's very good to have a different mode for when you're flying. The autopilot it's very convenient for an autopilot to function in one way when you're flying, and in a very different mode when you're landing. You need basically different inputs, you have different priorities, you have basically a different system. So these kind of equations that we call conditional equations or guarded equations are ones that can decide on which mode or which kind of conditions we're operating under. Discrete jumps allow us to model even the simplest mechanical behaviors. So if you go back to your physics class, when you were in high school or college or whatever, and you think about two different classes. One was about the acceleration when you throw something in the air and how long it takes to fall, and the other was about two cars colliding together and the momentum before and after. One is continuous and the other is discrete. In physics class, you rarely put these two things together. In the real world, you pretty much have to do that. Yeah? Because whatever thing you threw is actually going to impact the ground and bounce at some point. So those things are going to be discrete jumps. And what's going to be discretely changed here is the direction of your speed. So in one case, the speed is continuously changing due to the acceleration effect of gravity. In another case, you are immediately or instantaneously bouncing back in the opposite direction. All of this together basically gives us hybrid systems. I'm giving you here an intuition. This is quite informal. I'm not going to give a formal definition of hybrid systems, but what I'm going to do from now on is to look at examples for how we work with these kind of hybrid systems to model. So the plan for today is we will use for most of the presentation a tool that we had developed in my group over the last 10 years called Acumen. And what we will do there is we'll talk about physical form, modeling physical form in an easy way. And actually, the goal is to show that we can do all of these things in an easy way. And more importantly, that when we do that, we're able to experiment with really important concepts and learn very important things about the challenges of building cyber-physical systems. This morning, Martin talked about complex cyber-physical systems. Here, we'll have a tool for thinking about challenges that arise even in simple cyber-physical systems. Yeah? So we'll start with physical form today, go to a simple mechanism for abstracting models and instantiating them. Then we'll talk about elementary mechanics, dynamics in particular, and also some elementary ideas from control and hybrid dynamics. Dynamics when we have discontinuity or conditional guards for equations. And tomorrow we can talk about discretization, quantization, something that is rather challenging, that doesn't necessarily happen when you have continuous or discrete separately, but when you put them together, you can have xenobehavior. And this can be challenging for a number of different reasons. And it's surprisingly easy to get xenobehavior. In fact, almost any interesting mechanical model will encounter xenobehavior as once we talk about this. Or this will be easy to see once we talk about this. Jeremy talked about formal verification methods, and enclosure-based simulation or reachability analysis is an example of a formal method that is intended to be as easy to use as simulation. So that's the idea. Okay, technically, there's a lot of things that make this a little bit more challenging to do than simulation, but if time allows, we'll talk about that. This is actually where most of our research is focused, and it is supported by the Acumen tool in some form, so if we have time, we will touch on that. And then, hopefully, tomorrow, we'll also have some time to talk about some models that you've created. So Acumen is available freely online, and Martin sent a link which has simple instructions for downloading it. The only tricky thing about downloading it and using it is you have to make sure that you have a particular version of Java. Is it Java 8? Java 8, thank you. The more recent versions, it hasn't been upgraded to work with yet. Okay. What's that? Huh? So let's jump to, by the way, feel free to ask questions at any point. Does anybody have any questions at this point? All right. Let me see if I can start my version of Acumen now. So usually once you've downloaded the zip file, all we need to do is to double click on this, and then we have that. All right. So we have a kind of an informal agenda for what we want to do, which is represented on this slide. So when you start Acumen, it looks like this. Does everybody see the text here? No? So we can make it a little bit in large font. Say, at the back, can you tell me when you see it? It's good? All systems are go? Okay. I don't think I can enlarge this one, but I can read what it says. It's hopefully something that I can respond to pretty quickly in real time. Okay, so this is actually a valid model. Model main of simulator equals initially and then empty. This is something that can be executed. It doesn't do anything, actually. I wonder if this is also a valid model. Yeah, actually, even this. So this is a model that does nothing. Okay, that's the empty model. So hopefully we can do something more interesting than that. And there's two parts to any model. There's an initially and an always. And for starters, we'll just say we want to use this special variable called underscore 3D so that we can visualize a box. And this is all we have to do do that. And when we run this model, we get something that looks like this. Okay? It's pretty straightforward. Good. Now, what else might we want to do with this box? We might want to give it some color. What is our favorite color? Blue plus red times 0.5 of that. Are we going to add more colors? There's a bracket that belongs to this one. Thank you. So let's try that. Ooh, it doesn't like that because I made a mistake. This is supposed to be a 0. So what it says expected something but found something else, which is understandable. Okay, so this is this color. All right, so this is red and blue. Maybe we go with just red for now? Okay. We can come back to mixes a little bit down the road. Now, other things we might want to do with this simple geometry. Let's say we want to build a car, a simple car. Yeah? So maybe we want to give it some length. How long is a typical car? That's a good point. So let's say 4. Yeah, okay. So then we just run that and, good. Okay, this is our car now. Are we done? It is a model of a car, that's right, a model of a 4 meter long car. So what could we do to help here? So we could say width maybe? How wide should we make it? 2.55. Okay, let's say 2. All right. I think we have some mechanical engineers or car fans here, but that's good. Should we go with 2.55? All right. I think this is good. How high should the body of the car be? 1. Height. I will go with 1. Yeah. I think this is okay. I think this is a pretty good car already. Yeah. Okay. A little bit very bright, but okay. So maybe we can also add a little bit more detail so that it looks a little bit more car-like. How would we do that? Maybe another box, slightly higher. Okay, we didn't say where we wanted to put this box, but there's an implicit parameter which is center, and by default that happens to be at the origin. So if we want to copy this box and make another one, now if the first one was 1 meter high, how much higher should we start the next one? 1 meter, yeah? I think 1 meter is good. Now, this brings up the question of what do these numbers mean? And if we put in the axis, we can't see it now, but actually the axis says this is x, this is, well, we can't see the x, but this is y and z. So we want to shift it in the z dimension. So we will say 0, 0, 1, and poop. Nope, there's a mistake. All right, what was the mistake? It said, I found a closing parenthesis that I don't like. Here, that one. As the designer of the syntax of this language, I do a horrible job of remembering what I should write. But the error messages tell you what you need to do. So this is not what we intended. Probably we don't want to make it as long. So then, okay. Is this a car now? Almost. Okay, let's go with this. Yeah, this is a good car. Okay, so this pretty much, there's a lot of shapes, and the way you find out about all the shapes is there's a reference manual. If you go to help, there's this reference manual here, and it has a lot of detail about all the kinds of shapes that you could build and how to manage the colors and all of these kinds of things. So it's all here. And once you download the software, you will be able to find it all in the same place. So now one thing that we could do that would be useful is to not have to, let's say we want to make 2 cars. That's always a good thing. Yeah? How do we do that? So we want to take this idea and do it twice. And one way we can do it here is to actually go back and call this model car. Yeah? And it doesn't have to have any parameters. And we can say, well, model main now, we don't need to worry about the simulator parameter. Initially has 2 things. C1 equals create car, and C2 equals create car. Okay, now we have 2 cars, and they're both right here. Yeah, this probably violates a safety requirement that we would like to have. So what do we need to do? It would be actually good to have a parameter called position, and say that wherever we put our car, we want to add this. I said position, so I should say position here. So we want these 2 different parts to be placed in the position plus these 2 different offsets. So now when we create the cars, we can say 1 car at the origin, and then where should we put the other car? Let's say we want to put the other car like next to it so that we can have a race. Yeah, that's also a good thing to have. So where do we put the other car so it's next to it? 0, 1, 0. Because this is the y-axis, right? Cool. 0, 1, 0, they would be standing right next to each other. Yes. Okay, maybe we can put them slightly apart. So 2. All right. Oh, interesting. That was not enough. Yeah, they are big cars. So maybe we can make them, it's the 2.55. Can we put them on diet a little bit? All right. Or 1.55. Okay. These are going to be thinner cars. Right? All right. All right. Yay, 2 cars. There's also something cool that we can do at this point, which is we had not decided exactly what color is the best color. So we can go and say color here. Well, actually, pass a parameter color here. And then say that we want the color to be, let's say, we could just say color when we instantiate these different parts. But we can also make it a little bit more easier on the eye by mixing it with white. Yeah? And if we do that, we should give a little bit different weights. So maybe 0.4 on the color and 0.6 on the, so that the total is 1. Total intensity is 1.
Question here about color.
Yep.
Can we use RGB code?
We are using RGB codes. So very good question. So red is just the triple 100.
I mean in numeric.
We can use it as well. Yeah, exactly. Good question. Is everybody familiar with RGB? Yeah, kind of. So if you want to play with RGB, this would be a good way to do it. Oh, something happened. Oh, I didn't say the color. So let's say this one is red, and what was the other color? Blue? Okay. So, okay. So we have a raspberry colored car and a blueberry colored car. All right? Cool. Okay, so I think this should conclude our geometry part. We haven't obviously covered everything about geometry, but at least we have a simple representation. Now, what was on our list? Let's check the list quickly. So the next thing was we've already done geometry, physical abstraction, or a simple abstraction instantiation, and then elementary dynamics. So here's a question. How would we get, let's play this game. So we're going to have this car lead and do something interesting, and then we're going to try to see if we can get this car to follow this one. This can be a simple platooning scenario, although in this case they're kind of driving next to each other. It could also be a more sophisticated scenario where the red car is the imaginary path that we want to follow, and the blue car is supposed to be following that path. So this can be a lot of different situations, but it will illustrate, we could use this to illustrate both key ideas from dynamics and also from control. So how do we get the first one to move like a car, like a mass at least? Any ideas? Simplest possible way. We need a position. We need to update it so it's changing, so we need a velocity. And there's going to be differential equations involved. And, velocities are a little bit tricky to manipulate directly because we can't just have physical bodies go 100 kilometers fast this way and then immediately change this way. So we have something that can be changed in between. It's called the physical thing, acceleration. So we're going to have a PID controller. Yes, that's true. But acceleration. So how do we do that? Well, we declare these variables by saying, let's call the variable associated with C1, x1. And initially we make it 0. And then the derivative, we need it, and we'll call it x1 prime. Actually, it's written x1 prime. And then we'll have x1 double prime as the acceleration. Yeah? So all of these things are zeros. If we say, run, it'll say you made a typo. Where's my typo? No equation specified. Oh, okay, it's not saying that there's a typo. It tells me, hey, you have these variables called x1 and x1 prime and x1 double prime. You don't define them anywhere in your model. Okay, so I need to do that. And then at this point, I need to start saying, well, always, I need to do something with x1 double prime. Let's say it's 1, and then run my model. Okay, nothing happens. Do we know why?
You haven't assigned it to anything.
I haven't connected x1. So actually this is really interesting because x1 and x1 prime and x1 double prime are all connected automatically. The system is doing the integration for us, yeah? Which goes from x1 double prime to x1 prime to x1. What I haven't done is connected my geometric model to my state variable. And if I peek into this plot, I will see a whole bunch of variables, mostly constant, but there are these things that are increasing. That's what the acceleration is doing. But I need to connect these things. And the way I do that is really easy. I just say c1 dot position has to be x1, 0, 0. Okay? All right. Is my work done? Let's see. I do that. The model runs. Ah, the car doesn't go yet. There's one more piece that's missing. And the piece that's missing is a little bit technical. But remember, I said initially draw this stuff. I didn't say what to draw afterwards. Okay? So in fact, I don't need to initially draw this at all. I can just say initially, underscore 3D is a special variable that draws things. I can say underscore 3D is empty initially. But then always have the underscore 3D after that be a box with the position that is derived from this parameter POS in C1. So once I do that, okay, good. The ship starts sailing from the harbor or the car, whatever. All right, cool. Now I have this behavior that looks like this here, but the other car has sailed away, and we can replay this animation if we want to. It's okay. We can do that. Now, in general, we don't want our cars to just accelerate arbitrarily, so we're going to jump directly from the simple dynamics that we've just expressed by having x double primes or second derivatives. That's kind of what dynamics is about, second derivative. Or in mechanics at least. When we say dynamics as opposed to kinematics, we mean second derivatives, accelerations. We generally don't want things to accelerate forever. We want to accelerate to get to a particular speed. So the way we're going to do that with feedback, very kind of simple feedback, is to do this right here and say we want to get to the point where x1, the speed, is equal to 10. This may seem a little bit magic at first, but this is the general pattern for modeling feedback. Yeah? So if, actually, did I have this wrong? Maybe I got this wrong. I could have the signs wrong. Let's see. The easiest way to check is to see what happens. No, it seems to be right. So basically, what we want is we want acceleration to be equal to minus 10, so like the value of 10, until x1 prime, the speed, is close to 10. By the time that x1 prime is 10, the acceleration is going to be 0. So we get this kind of effect here. The plot shows all of the variables. One nice trick to not show everything is to say underscore plot empty in things that we don't care about. So if we run that, underscore plot equals empty, sorry. If we run that, then we get the same effect, but then the variables, we just see the variables in focus. When we point at this one, it tells us that this is the variable x1, the first one, and it'll give us the xy positions, the time and value of this. And then if we go down to the next one, this is the x1 prime, and this is the x1 double prime. So you see, the speed gets very quickly to close to 10. And the acceleration starts large, but also very quickly goes down because we're getting to our target. So far, so good? Yeah?
How do you get to know the meaning of these plots? So you don't have any label or legend on it.
Yeah, so they are not intended for printing. They're intended for interactive use. So the most important thing is to get a picture of what's going on. And then if you want to get the specific value at a certain point, you just point to it. And it'll say exactly what it is to all the floating points. Yeah? Remember, if you put a scale, you don't necessarily know the exact point values either. But it's a stylistic thing. Yeah? That's a good point. So let's say, so this is my animation now, and I can replay it. Let's say I want to go instead of to reach a speed of 10, I want to reach a speed of 20. What do I change in this model? What's that? Okay, which part of the acceleration? So this is the equation that defines the acceleration. What do I? Make this minus 10, minus 20. Great. This is the magic constant here. Yeah? So it goes faster. Yeah? And then here it approaches, it's 19.92, very close to 20. All right. Now, we're done with this. How do we get the other car to follow this car? We don't want to tell the other car anything other than follow that car. You've seen this in movies, right? Okay, so.
But you can use the same function as y.
All right. So we can say we make ourselves a bunch of variables, yeah, or actually a variable and its derivatives to help us, and we could, of course. So you're right. So exactly. So in this case, we could just take the very same state variable, and then use that. And so let's do that first. Yeah. Okay. Thank you for bringing that up. So actually, before doing anything else, we could say c2.pos equals x1, 0, 0. I think this is the one that you were suggesting, right? Or?
My idea is just to plus some pixels on that.
Okay. So actually we start off at 0, 0, 2, so we put the same x and then the offset, yeah? So this looks like this. And then both are going, okay? Now, this is a model, right? But maybe it's not quite the model that we're thinking about when we're thinking about platooning and one car following another car. Because the red car is following this idea or target of reaching the speed of 10. Yeah, that's the story that this equation is telling. The story, or 20, but let's make it 10 so that we. So the story here says that x1 is representing the position, and x1 prime is representing the speed, and x1 double prime is representing the acceleration of the red car. Yeah. What we want to model now is one car trying to follow another car.
Only the starting point will be different. The rest of it should be the same.
That's still a very idealized one. If I do that, if I do what I do here right now, this means that C2's position is exactly C1's position in this dimension. This is something that's very hard to realize physically. It's one thing for me to make an object that has a plan for moving in a certain way by itself. It's a very different thing for me to expect one object to know where another object is. Yeah? So if I have autonomous vehicles that knew exactly where everything else is on the road, that would make life so much easier. Yeah? Autonomous vehicles would be so much easier. But it's very difficult for us when we're thinking about the behavior of one object, yeah, to assume, to figure out how to talk about another object. And this is what we want to do here. And keep in mind that this is a little bit of a tricky thing with modeling, is that we could just easily write x1 here, but it's modeling something that is physically very hard to realize, that one object knows where the other object really is. Exactly. So what we'll do is we're going to say we have another position called x2, and we're going to make a whole bunch of state variables or variables that represent this object's position. I just need to copy and paste without creating too many problems. So just like we have the x1s, we will have x2s with their derivatives. This live coding stuff is fun, but kind of error prone. All right. Sorry. So this, here I have a model, and if I run this model, it'll complain again that I don't have equations specified for x2. But if I think as somebody who knows a little bit of control, not too much, then what I will do is I will try to track the position and keep track of the other object's position, keep track of my position, and try to minimize the error between these two. Okay, so one way to do that is we can take this equation here, and do a kind of simple PID controller like somebody mentioned. So I can control my own acceleration. So x2 double prime, I can define it. And what I can say is, well, look at where x1 is and compare that to where x2 is. And then basically, make the, I put a negative here out of habit, but basically this is going to be positive if x2 is greater than x1. Yeah? No, but that's not what we want. We probably want it the other way around. So we want it to be positive with x1 and to be compensated, to be reduced when x2 is closer. Yeah. So let's see what that does. So we run that, and we're going to get this effect. So actually, the blue one starts moving to catch the red one, and then it beats the red one, and then it slows down again. Ooh, what's going on here? Okay? So this is kind of the right starting point for building a controller for this kind of situation. If we look at the graphs, everything is kind of going okay with the position of x1. The speed also looks like it's still going according to plan. It gets close to 10. And the acceleration also winds down as we get close to 10. But then the position of the other one is kind of funny, and it's doing this wavy thing. Okay? It's not very stable. So if we see something like that, what do we do? What does the second car doing? What's going on with the second car? Here's what happens when we look at it. What's going on here? It's overshooting. It's kind of overreacting to things, right? So it's like, oh, wait, I'm too far behind, so I press the gas and I go really as fast as I can, and then I overshoot, and then I have to press the brakes again.
Decrease the P.
Decrease the P. Okay, what? V, D, E, what are all these variables? Oh my God. Okay, I didn't know that there were all these variables here. So you guys are using correct terms to talk about this idea of PID control, proportional. We got the proportional part, kind of. I don't know. Actually, I think this is the proportional part. Yeah? And then we need to do some I and D, integral and derivative. Intuitively, we need to dampen this effect. Yeah? So a lot of times the way we dampen things, at least in simple cases, is by using the derivative. So if we subtract the derivative of what we're looking at, so we take x2 minus x1, but actually take the derivative of both of them, then what this will do is when we pick up speed, the speed will work against our acceleration. As opposed, whatever speed we have will be reduced from the acceleration that we're sending. And again, I may have gotten these backwards. Yeah, okay. So this is kind of looking better, actually. So maybe I got it right. Yeah? So now this wavy thing that was here is much better. Yeah? There were some comments I didn't... It does go over, yes. It's very hard to be not over and not under. Yes, exactly. So, I think I can do this. Sorry about this. Let's add a variable just for the purpose of tracking this. If we want to capture the difference, so if we want to have, let's start this with 0, but say that this z is equal to x1 minus x2. Yeah? So when x1 is ahead, this will be positive, and when x1 is behind, it'll be negative. So this is the difference. This is the z variable. So initially, we can be 4 meters behind. Yeah? And then we do overshoot. This is what you guys were pointing out. Somebody was saying we overshoot, right? So if we click on this point here and extend it to there, we see that the curve goes like this. If we zoom in, the curve goes like that. And the blue line is the 0. So good job on catching that. What can we do to...
Increase the response time. Lower P, increase
All right. So here's the P and here's the D. Yeah? So this is called the P, this is called the D. What we're going to do is, if we want to cut down a little bit on this 4 is too big, and then we go overshooting. So maybe we do like, I don't know, we can put like 10 times here. magnify this error. This is kind of something that you could do with PID control. Respond more aggressively to this difference between where I want to be and where I am. What happens when I do that? We can see it visually first. Okay? It responds faster. And if we go back here, okay, this instead of being 4, it's now just 1. If you're wondering where I'm looking to get these numbers, the reading is here. This high peak here on this one is now 1. So we cut down on that a lot. How far can we go with this game? Maybe we put another 0. Oh man, they look really close. But you also notice they have a little bit of oscillation. Yeah? There's also a price to this, which is if you look at the acceleration, you could be, where's the acceleration on? Oh, this is the acceleration. You could be looking at pretty big values. So look at that. The value for the acceleration is 15. If we use these big constants, you're asking the car to really accelerate really fast. Gravitational acceleration is about 10. 15 is 1.5 g. Your tires will probably be skidding at that point. Yeah? So maybe this could work, this could not work. But let's try to get rid of the bouncing here, the overshooting and going back. How do we do that? We have something sitting in front of us. Remember, we said that this term dampens. Yeah? So we could just try to increase the dampening a little bit by, say, 5 times and see what happens there. Does it look better? Yeah? We can make this part of the screen a little bit better, run it again. Does the start look better? Yeah? Yes? No? Yeah? Looks better? Okay, cool. So if we look at the plot, sure enough, the overshooting is, the oscillation is reduced a lot, and the overshooting seems to be gone. We don't seem to ever exceed, the blue one doesn't exceed the red one. Okay? What about the acceleration? The maximum acceleration is down a little bit from 15 to 12. We could probably dampen a little bit more without anybody, without having big problems. Notice that the dampening, the size of the dampening term, that's just a computation in the controller that's running this computation. What comes out as acceleration, as how much power you're sending to the tires, that's a real torque. Yeah? So it's okay for us to use a big factor here, even if and it could be okay to use a big factor here, as long as on balance they seem to be doing the right thing. And the total is not too big when it comes to what's actually produced. So now the curve looks a little bit like this. The maximum acceleration is 11. Okay, at least it's closer to 1 g. That's still pretty fast. That's still pretty high acceleration. Okay, so we have about 5 more minutes maybe. Yeah. So one thing that we can do, we've talked about elementary control, we can do hybrid control, and then we're just on target. Notice the model for all of this is still quite short, and a big part of it in this case, actually all the dynamics is still fitting on this simple box. One thing that we could do to illustrate the hybrid nature of things is going back to your physics class, where you study the problem of throwing something in the air and where it falls. Well, what happens after it stops falling? There's an event that happens. So how do we capture that here? It turns out if we go to this equation that's driving the acceleration, that's controlling the acceleration, let's say we want to model, instead of just this kind of simple cruising activity, we want to go to this point where the car is, no, this is the position. Let's say we want to go to this point where the car is here, has passed the 20-meter mark. And then what do we want to do? Let's say this is the end line, or there's a curve in our racetrack and we need to turn. What are we going to do? Reduce the speed. You said brake. Yeah? So braking is a really good thing after you've been accelerating, especially if it's a really sharp corner, for example. Or, maybe more practical scenario, a pedestrian stepped in front of the car. Yeah? And we're platooning. We'd like everybody to stop. So the way we're going to do this is we're going to say if x is less than 20. In the pedestrian case, we have a condition that says there's a pedestrian suddenly there. Yeah? Here, we're just a marker on the road says, here's 20. If x is less than 20, we're accelerating. And we should say x1 probably. Else, x1 double prime equals how fast should we accelerate? Let's say minus 10. Yeah? Now, is this a good model for braking? Yeah? All right. So if we're before this milestone, we follow our equation. Otherwise, we're braking at minus 10. I should say minus. Okay, we go with that. So on your marks, get set, and the race starts. And look at that. We hit the 20 sign, and oh. Actually, this is funny. So what's going on here? What's that? So what happens is we go to did we say 10 or 20? Actually, we said 20, but this one, no, here 20 happens here, okay? So we reach the 20 point, and then we start braking. And then guess what happens? So the braking is the minus 10 here, and then the speed starts going down, and then it becomes negative, and then the car starts moving back, and then guess what happens? We're less than 20 again, right? So then we start running the controller again, yeah? So this wasn't exactly quite what we wanted, but it's consistent with what we wrote. Yeah? So here we have a model. We've just created a model of the behavior that we want, braking, which we said, well, it's decelerating at minus 10. But we actually didn't think about all the other things that happen when you're decelerating, including the fact that when you decelerate past stopping, you start going backwards. We don't want that. Yeah? Because that also did a whole bunch of things that were surprising. But it was interesting. And notice that the most important thing that I want to kind of communicate at this point is how easy it is to introduce events and to mix conditionals with equations. Yeah? This is very powerful. And this is the essential thing that we get from hybrid systems. This is it. The ifs with the equations. There's this one more tweak, but it's a small tweak. So how do we fix this behavior? That's not what we wanted. Can we make this model a little bit better? What's that?
We can if velocity goes minus, then make it 0.
If x prime, yeah, if x1 prime, where's my prime, is greater than 0, yeah, great.
Actually, it's 4.
What did I say?
All time. So it's 4 rather than if.
A for loop.
Yes, 4.
Ah,
Better than
if is better than for. So that's an excellent point. And this is tricky because so you're saying everything. I don't need to say anything. So that's exactly it. All right. So these equations, their semantics is that they should hold all the time. Unless they're under a guard, like an if statement, then they stop. So basically, the if can be read as a while or as long as, but it's a very powerful combination. The equations, even if they are discrete equations, sometimes you can write equations about discrete relations here. And with the ifs, you can do for loops and while loops and if statements and all of the computation stuff with just the if and discrete equations. Yeah? So very, very good points. Now, is this going to work? Okay, let's see. So we press play. And okay, it looks like they're working. All right. Accelerated, stopped, and then this is the braking and this is the stopping. And here's our other car trying to keep up. yeah, with all kinds of interesting things happening in a very simple model. And this is not even the whole story. This is just the beginning. Because guess what? There's really interesting things that can happen between these two cars. For example, if we're doing control, we're probably doing it using a computer. And a computer needs time to process things. So we're not going to be able to couple these equations the way we're doing here instantaneously. We're actually going to have some sampling and some delay. And we're only going to sample at a certain frequency. And we're never going to get these things very precisely, either because of the way we quantize things or because of measuring error. These two effects, discretization and quantization, basically, can also be modeled with if statements. Yeah? And it's going to be really interesting to see when we start doing that, what's going to happen to these two values at the bottom, the positions and the accelerations for the car that's following. So for next time, please take this model or any model and start exploring things that you are interested in, and let us know about it during the next lecture. Thank you very much.